Hi everyone. Today we are going to see how to model a plate in the LS-Dyna and see how we can get the output of this plate and compare it with the manual calculation for the plate using plate theory. Well, now our problem is that we have a plate of 4 meter by 4 meter. This plate is simply supported in the four edges, and this plate consists of a steel material with a thickness of 0.05 meter. So let's get started, see how to model that in LS-Dyna and then get the output. Okay, first thing we are going to create the shell element. To do that, we are going to the element, add mesh, and in element and mesh, I'm going to the shape measure. And shape measure offers you many templates that you can use it. For example, you can make a box solid, you can make a box shell. This will create a box of 6 edges, but it's empty from inside. What we are want to do is the 4-node shell. We most likely will go through some of these options in the later tutorials. So I'm going to pick 4-node shells to create our my shell element. For the 4-node shell, here he asks you about the coordinates for this 4-node shell. So let's go here and let's assume that this point is the 0, 0 coordinate for my plate element or my shell element. And as you know that it's because we are solving a shell element, so are we dealing with 2D elements. So we are dealing with xy coordinate, but the z is equal to 0. So this point will equal to xy will equal to 0, and this is my first point. So here I'm going to put 0 for the x coordinate, 0 for the y coordinate, and 0 for the z coordinate. Now the next point, which is in here, will be y equal to 4 but x equal to 0, so it will be 0, 4, and 0 for the z. Now for the third node, x equal to 4 and y equal to 4 but z equal to 0, so we will go here, y equal to 4, z equal to 4, and x equal to 4, y equal to 4, and z equal to 0. And the latest point, which is located in here, x equal to 4 but y equal to 0 and z is 0 as all of them. So it's y is 4, z is 0, y is 0, and z is 0. Now he asks you here about the number of divisions that you want to divide your plate to it. For example, this 4 meter, how many divisions you want to be divided. This is the nx, and the ny, how many divisions you want to divide the y direction. So here I'm going to make an element of 0.5 by 0.5 size, which means that I'm going to divide my x direction to 8 elements and my y direction to 8 elements. And then I'm going to click create. As you can see here, this is my shape of the shell after divisions. That's it. Okay, accept and done. Now after we create our element, we want to go through the definitions. So first I'm going to model and part tab, and in model and part tab I'm going to keyword manager. In the keyword manager, as usual, I'm going to click all, so I will see all the lists, and I'm going through the definition step by step. First I'm going to define the material, then I'm going to define the section, and then I'm going to attach the material and the section for the part of the shell, and then complete our remaining definition, which containing the load and the boundary condition. So let's go first for the material. And in material we will use elastic material, and I'm going to name it as a steel. The elastic model, the density is 7850, the elastic model is 2E11, and the Poisson's ratio is 0.43, and accept and done. Now for the section, this is a shell element, so we are going to shell section. In this shell section, first I'm going to name it as a shell, and here we will have many definitions for the element formulation of the section ID, same as the beam. You can go to Wikipedia and search for each one of them, what is remaining, what is meant by, and for our case we will go to element number 16, which containing the fully integrated shell elements. And after we finish our model and run it, we are going to test one of these elements to see how choosing the element is very important, how choosing the element formation is very important to your case study. So for our case study, we are going to use shell element, which is 16 element formulations. And now after that, we will go here in the number of integration points. This is splitting. For example, we are dealing with a shell element. If we go here for the shell element, after finishing that, you will find that the shell element have no thickness. This option asks you about how many divisions you want to divide your thickness to make the integration for. Most manuals recommend to use number 5 for elements. If you want more higher results, higher output values, you can increase this value, but number as a 5 integration point is very enough for us to have very good output. After that, we are going to define the thickness of our plate, which is 0.05 meter. And here we have a new thing that we didn't notice before in LS-Dyna. As you can see here, this is marked with a red. The red tabs in LS-Dyna or in the keyword input, if you change it, then it will change the remaining thicknesses. For example, if I click in here, you will find that the thickness of the plate at the 4 ends become 0.05 and 0.05 and 0.05 and 0.05. What is T1, T2, T3, T4? If we pick any of the shell elements, for example, this is our shell element. So this is node number 1, 2, 3, 4. And then when he's going to take his thickness, he will make this thickness 0.05, and this one is 0.05, and this one is 0.05, and this one is 0.05. If you have a special case, you want to change your thickness, you want your thickness to be varied from point to point, you can create it as you wish. Okay, we're gonna accept that and done. So now we define our section and we define our material. Now we want to attach the section and the material for this plate. So we are going to parts and we will find our part list, and in our part list we'll find the shell 4 part, which this is referred to the part that we have created in here. I'm going to change its name to shell, and in the section I'm going to pick section shell, and in the material I'm going to make steel and accept. We almost there, but right now we want to define the load. In this type we are going to define a new type of loading. It will not be a concentrated load. We will define here the own weight of the shell as the load. To do that, we are going to load, and in the load first you have to define a list of the parts that you want the LS-Dyna to include when he is calculating the own weight. For example, here we have only one part, which is the shell. But for example, if you have a complicated model and you want to include some of the own weights and some others you didn't want, so you have to make this list for the elements that you want the LS-Dyna to calculate the own weight. So to do that, we are going to load, and then we are scrolling down until we find body parts. And I'm going in body parts, and here, as I told you, he asks you about the part list for the element that you want the LS-Dyna to include the own weight in his calculation. So to do that, I'm going to pick in here, and I'm going to use a new entity to define my part list. And in my case, I'm just going to pick this part and click, for example, own weight to define this list, and apply. So this is the list that the LS-Dyna will start to calculate the own weight for, and I'm going to accept that and done. So right now I defined the list only, but I didn't define the load for the own weight. So to define the own weight itself, I'm going to body Z, and as you can see here, there is body Y, body X. For example, if you have an acceleration in the X direction or Y direction, for whatever is the application, how it goes, so you can define it too. But in our case, we have only an acceleration in the Z direction, so I'm going to click body Z. And in body Z, first here he asks you about the load curve ID. How is your definition of the load will go. So I'm going to click in here and make a new keyword as we did before and define curve, and I'm going to define the load curve, and as usual I'm going to make it at 0 equal to 0, at 1 equal to 1, and at infinity 1e28 is equal to 1. So this is my load curve, it's a ramp, and then I'm going to accept this load curve. So this way I define my load curve. Second, he asks you about the scale factor, how you want to scale your what is your scale factor for the loading or for the gravity. Actually our scale factor will be the gravity acceleration, but to put the right number for the gravity acceleration I'm going to focus on that again. Be sure about your units. All our units here is kilogram for the masses, meter for the dimensions, and Newton for the forces. So to do that and to be sure about that we pick the right value for the acceleration, I'm going to the units again, and as you can see here I'm using the first row, which is kilogram for masses, meter for lengths, second for time, and Newton for forces. If you choose these units you can find that your gravity will equal to 9.806. This is very important actually, you have to be careful about it. So I'm going here to put my gravity as 9.806. This is how I define my gravity, and you didn't have to put it in negative, that it will automatically apply it in the negative z. So I'm going to click accept and done. To sure about that, if I'm going to scroll my view, so the load will be in negative z direction, it will be in the vertical direction. Let's go back again to top view. Right now my model is ready to run, just I have to define the boundary conditions. So I'm going to close this, and as we do usually we define the boundary condition using create entity. So I'm going there and I'm going to show my list, and I want to make a boundary for the SPC, and we said that it will be simply supported at the 4 edges, so it will be easy to check using the plate theory to check is our movement is right or not. And then I want to select the whole coins in the edge, and to do that we are going to use area in the selection, and then we are going to mark around these points and these points and these points and these points. For example, if you pick some wrong nodes in the middle, so to make unselect you hold the right mouse button and make a window, and it will make an unselect for these nodes. Now I'm going to click apply. So this way I create my boundary conditions for the slab, and then I'm going to close the create entity and going back again to the keyword manager. Now our model is ready to run, just I'm going to define the termination time and the output. So I'm going to control and going down in termination, and I'm going to run the model for just 2 seconds. Accept and done. And for the output in the database I'm going to use as usual D3 plot, and I'm going to make a decrement of 0.01 for the output, and accept and done. Now my model is ready to run, so I'm going to save it. And I'm going to name it as a shell model. Save. And now we are going to run the model. As you can see, we are done. So I'm going to close it. And let's see the binary D3 plot file. So file, open binary D3 plot file, and we choose our output. Now if we're going to show the 3D view for the plate so we can see how the deflection looks like, and we run the model. Oh my goodness, there is nothing is changing here. Actually, it's because of the scale of the output. So to increase the deflection scale, we will go in the pre-post and we will go down in settings, and you will find in settings displacement scale factor. And what is good in displacement scale factor, for sometimes we can see that, and we will make this in later videos, that some elements have a very high displacement that you want to show it, and the others you don't want it to be affected by this displacement. So you can here choose if you want to apply the scale for the whole view or for the whole elements or just for a specific part. I'm going to choose a specific part. I'm going to pick this part, and I'm going to tell him make a scale factor of 1000, apply, and here you can see the deformation of your elements. Okay, this is the displacement. Now we want to check the moment of the shell element. So let's first go and see how is the manual calculations goes, and then see how to check this moment. So if we go for this element, it's a 4x4 element. To solve this using a plate theory, first we are going to calculate the weight. So to calculate the weight, we are going to times the density of the steel, times the thickness, and times the width and the length of the plate. And normally when we try to solve that, we only take one strip of 1 meter and solve it, which is exist in the middle, same as here, and solve it as a simple beam this way. So to get the load in this strip, we are going to find the load for a 1 meter by 1 meter portion, which is equal to 750 times the thickness, which is 0.05, times the acceleration, the gravity acceleration, times 1 by 1, which is the width and length of the strip. It will equal to this value. And then we are going to, using the as a reference, the plate theory, say that this force, 35% of this force will be transmitted in the horizontal direction, and the remaining 35% also will transfer in the vertical direction. That means that 70% of the load is transferring horizontally and vertically. Well, that means that there is remaining 30% of the load. This 30% of the load is transferring through the torsional distribution in the plate itself. So if we calculate the force, so for the flow force going in the horizontal or in the vertical direction is equal to 35% of the total load, which is equal to 1220 Newton per meter. And then we are simply we're going to take a horizontal section or a vertical section in these two plates and deal with it as a simple beam. So in this case, we have a section of a 4 meter with 1220 Newton per meter load. For this calculation, if we calculate the moment, it will be equal to 2440 Newton meter per each meter. This force or this moment is for each 1 meter width of the strip. So the moment is equal to 2440 for 1 meter width horizontally and 204,040 for 1 meter width vertically. So this is our moment in the horizontal and vertical direction. So how to see that in LS-Dyna, to check if we have the same values in LS-Dyna or not. So to check the moment values, I'm going to stop it and scroll the cursor until the end of the time. To check the forces and the stresses, deflection, everything you want, you will go through fringe component. In the fringe component, you will have many things that you can check. For example, you have the X stresses, Y stresses, D stresses, many things that you can check. Here what we're concerned about is the resultant. And in the resultant we have mx and my. So what is mx and what is my? To check what is mx and what is my, we'll go through this illustration. So imagine that this is our shell element and this is our xyz coordinates. So the moment which is parallel to the x coordinate, which will be affect in this as it's shown in here using the right hand rule, this will called an mx, and the moment which is in parallel to my according to the right hand rule will called my. So this moment is bending the slab in this direction, which is my, and mx is bending the slab in this direction. So if we go back in here and we choose mx, so mx according to the right hand rule will be rotate around the x-axis, so it's bend the slab in the vertical direction. And the moment mx is equal to 2800 Newton meter, which almost there is some difference between these two methods. This is approximately give you the number of the moment approximately, so there is some difference between both of them, but what is good that we are around the correct number. So this is the number of this is the value of the moment in the x diet in the around the x axis, and for the moment in the y axis it will be with the same value. Now after we finish that, for example, if you want to, this is the maximum value for the moment which is in the middle. For example, if you want to get the moment for an element in a specific location, how to do that? And instead of using the fringe, you are going to plot the history of the element. What is good in the history, you can plot anything you want. For example, if I want to plot the displacement of the node in the middle, so I'm going to click nodal, and in the nodal I'm going to click z coordinate, and then I'm going to pick this node and then plot. And as you can see here, this is the displacement of the middle node. And what is happening here is because we define our system as a dynamic system, and we didn't define any damping for factors here, so it excites around its static displacement. Later we will discuss what called about implicit and explicit solver. So in explicit solver we can have a straight lines because we solve it as a static problem. And as you can see here, this is the displacement in the middle nodes. You can pick some other nodes in here, plot, so you'll have a lot of different curves, and then you can choose what you want to see. Okay, this is for the node. What about if I want to plot the moment as we did before? So I'm going to click element, and in the element you have to choose here element type as a shell, so he will give you here the shell element functions. And in the shell element function you can see, if you scroll down, you will find mx moment resultant. And then I'm going, for example, to pick these elements and plot. And as you can see here, the one in the middle give you the highest value, which equal to 2.8 as shown here in the maximum fringe or the minimum fringe value, and the remaining moment is different according to the location of the shell element. Okay, this is all about how to define an on weight for a shell element and how to see the moment and how to plot it, to plot the history for the moment for any element. Now we are going to make a small test for this element. So for example, I'm going to close this element, and we are going to take a copy from this file, and we will change the element type. As we discussed before, that the element type, the element formulation is very important when we choose our section. So you go in section, shell, and instead of using element formulation number 16, I'm going to use the default, which is number 2. And let's see how this will affect the results. Save the file, and then run the model. As you can see, it's much way faster than before. And now let's open the binary D3 plot file, and let's see how the deflection looks like. So we have to increase the scale factor as we did before, and I'm going to leave it as a whole. Apply. Oh, let's check it again. I think I opened something wrong. Okay, let's see the deflection. Make it 1,000. And we run the model. We can see that have the same deflection as before for the same model. Let's see the moment. If we stop it at the end of the run, we can see that it's almost it increased about 100 newton meter, but almost give us a very good results. So actually this is very good that we have run the model in a shorter time using another element formulation, and we can save time using that. So picking the right element for your model is very important. You have to choose which element you want to bake according to the time that you expect that to run the model on it and the capacity of your PC. Hope that it was clarify anything and how to make the model for the plate element. And wait, just if you accept that, you just subscribe in the videos and wait for the next video next week. Thank you very much.